Higher order derivatives, these were actually introduced in section 2.2, but I'm covering them here in 2.3 because they're so much more fun once we have the derivative laws. So a little flashback to 2.2 to bring back this topic. So higher order derivatives is, remember, when we take a derivative, we're getting a brand new function that's a function of on its own right. So we can take a derivative of that function once we've taken the derivative, we get a new function, and then we can take a derivative of that function, which gives us a second derivative, and so on. So here's some notation for that. So we talked about, we've used this notation for first derivative. We used f prime. We've used y prime. We've used the dy of dx. For a second derivative, we use 2 primes. And on this notation, we put the second derivative in respect to x both times. So the 2 goes on on the numerator, the number goes on the d, and the denominator goes on the variable that's being taken in respect to. Third derivative, so on. You'll see this kind of pattern. So we put the third derivative taken in respect to x all 3 times. And sometimes we use n if these numbers get really big, or not, sorry, like if, for example, if I have like the 50th derivative, then I wouldn't write 50 tick marks, I would just use the number 50. And so on. All right, so one good application, a common application of this is the position function. The position function, when we think about what is position, the position function, we'll call it S, is, well, it tells you where you are. And the velocity function, so if I take change in S over change in time, how long has let's see, change in S is change in position. So how fast is my position changing? What is the rate of change of my position in respect to time? So that's our velocity. Now, if you're going a certain speed, so you're driving 45 miles on the freeway, 45 miles per hour, and you need to go faster, what do? So what is the change in velocity now? The change in velocity, I need to change my velocity in respect to time. That becomes acceleration. So how fast is my velocity changing? So if I slam on my accelerator, that number is going to be high. And if I just kind of gently tap it, it'll be low. If I keep going with this, I'll get j of t, which is the fourth derivative, which is jolt. So if I think about change in acceleration in terms of time. So if you slam on or if you push your accelerator really hard or slam on your brakes, you're changing your velocity very quickly, which would give you a jolt. But if you accelerate very slowly, or if you just tap on the brake and slowly slow down, then your jolt would be very low. So this is our fourth derivative. Oh, sorry, the third derivative. Third derivative. So how fast are you accelerating or decelerating? All right, so let's imagine a particle measured in seconds. So this measures its displacement measured in centimeters. So our units are going to be centimeters per second. So our velocity, that's how fast our position is changing. So that makes sense that that would be change in position over change in time. So to find that, it's really the derivative of s. So if I have s of t equal to 2t cubed minus 5t squared plus 3t, now that we have all these derivative rules, I can apply the sum and difference rules. I can apply the power rule. I can apply the constant multiple rule, and I can derive this really easily. So the velocity can be measured as the derivative of s of t. So I'm going to just scoot that over so my numbers line up. So the derivative of 2t cubed, I take my 3 down, I multiply it, and I get 6t squared. 5t squared, I get 10t. 3t, I just get 3, and my 4 turns into 0, so I don't even need it. So this guy measures displacement, where he is at any given moment in time. And this one shows the movement, how fast is it moving, and in what direction. So that gives me an equation for that. If I know the time, I can figure out how fast the particle is moving and in which direction. And then I take the derivative of that. So I'm taking the derivative of the velocity function. Taking the derivative of the velocity function, which is the second derivative of the position function. So taking the derivative again of the brand new function, I get 6t squared becomes 12t, negative 10t becomes negative 10, and my 3 turns into 0, so it goes away. So this is my acceleration. Which is really dv of dt. So it's the derivative of the velocity, or the second derivative of the position. Let's see, so now let's think about our units here. So our displacement should be, that's just the meters, that's just the amount, where it is in space in respect to the origin. So that one would just be centimeters. Velocity is going to be about speed. So how much has it changed? So that's change in s over change in t. So how much distance has traveled over seconds? That s is for seconds, not the variable s. And then my unit on acceleration, so that would be centimeters over seconds squared. If I wanted to find the jolt, that's not on this exact, so this is a little extra credit here, a little extra just for fun. If I wanted to find the jolt, then I would take that acceleration function, which would be the second derivative of the velocity function, or the third derivative of the position function. Those are all the same thing. And I would just kind of look at my most recent function, the accelerating function, and I've already taken the position function twice to get here. So to get the third derivative of this position function, I take the derivative of this, which is just 12. So a little bit of a jolt. Jerk, sorry. 12, I think that would be centimeters per second cubed. It's called jerk, not jolt, sorry. All right, let's look at B. What are the velocities and accelerations after 2 seconds? So now I can take the functions I just found and plug in 2 for t and find out what the velocity is and what the acceleration and what the jerk is if I want to. But that was extra credit. So our velocity at 2, we're just going to use that function. And our function that we found for velocity is right here. plug that in over here. We get 6 times t squared, and now our t is 2, minus 10 times t plus 3. And simplifying that, I get 6 times 4 minus 10 times 2 is 20 plus 3. Or 24 minus 20 plus 3, which gives me 4 plus 3, or 7. And again, my units for velocity is centimeters per second. All right, and my other question was acceleration. So for acceleration, we're going to use this function. So our acceleration at 2, I plug it into the 12t plus minus 10 with t equal to 2. And I get 24 minus 10, or 14. And again, my units on acceleration here would be centimeters per seconds squared.